Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to talk about calculating heat quantities. We're going to calculate heat quantities in terms of refrigeration and air conditioning, and we're going to talk about specific heat and latent heat. To start off with, specific heat is defined as the amount of heat absorbed by a substance when increasing in temperature. We're going to be using the English system, so that quantity is going to be measured in British thermal units, BTUs, and because we're working with imperial units, the weight will be in pounds and the temperature in degrees Fahrenheit. So different substances have different specific heats. Water, for example, requires 1 BTU of heat per pound of water to increase by 1 degree Fahrenheit. Ice requires 0.5 BTUs per pound per degree Fahrenheit. If you were to look at a metal, it might be 0.1 or 0.2 depending on what the metal is. So every substance will have a specific heat, the amount of heat required to increase the temperature of that substance by 1 degree if we're dealing with 1 pound of that substance. So the total amount of heat required is going to depend on the specific heat, the weight, and the temperature increase. So we're going to use these letters in our formula. Heat quantity is measured in BTUs, will equal weight, which is measured in pounds, times specific heat, which will be given for that particular substance, and this is the unit that's involved. Delta is a symbol that's used to mean change, so this means change in temperature when you see delta T, and that's going to be in degrees Fahrenheit. Let's take a look at an example. Using this formula, let's find the amount of heat required to raise 20 pounds of water from 35 degrees Fahrenheit to 95 degrees Fahrenheit. So that amount of heat, H, will be equal to the weight, which is 20 pounds, times the specific heat of water is 1, times the temperature difference. So we subtract 95 minus 35, that's an increase of 60 degrees or a temperature difference of 60 degrees. And now we simply multiply these and we'll get 1200 BTUs. Now let's talk about latent heat. Latent heat is the amount of heat required to change the form of a substance. So for example, if we were changing ice to water, that's called the latent heat of fusion, and it's the amount of heat required to change 1 pound of ice at 32 degrees Fahrenheit to water at 32 degrees Fahrenheit. And that value is 144 BTUs per pound. Similarly, if we were changing water to steam, that's called latent heat of evaporation, which is the amount of heat required to change 1 pound of water at 212 degrees Fahrenheit to steam at 212 degrees Fahrenheit. That's the temperature where water changes to steam. This is the temperature where ice changes to water. And the value for the latent heat of evaporation is 970 BTUs per pound. So let's take a look at an example where we start with ice at a certain temperature and we want to heat it up so that it changes to steam at 212 degrees Fahrenheit. Our question says how much heat is required to convert 30 pounds of ice at 20 degrees Fahrenheit to steam at 212 degrees Fahrenheit. So we're going to need all of this information to do it, and our first step is to heat the ice to 32 degrees Fahrenheit. To calculate that, we're going to take the weight of the ice, which is 30 pounds. We're going to multiply by the specific heat of ice, which is 0.5. And we're going to multiply by the temperature difference to take it from 20 degrees Fahrenheit to 32 degrees Fahrenheit, which is 12. We're going to multiply that out and get 180 BTUs. Now it's ice at 32 degrees. We want to figure out the heat required to change it to water at 32 degrees. And in order to do that, we're going to use the latent heat of fusion. We're not raising the temperature, we're just changing it from ice to water. So that's going to be the 144 BTUs per pound, and we have 30 pounds, so that will be 30 times 144, 4,320 BTUs. Now we want to raise the temperature of the water from 32 degrees Fahrenheit to 212 degrees Fahrenheit. And in order to do that, we're going to use this formula again. The weight is 30 pounds. The specific heat of water is 1. And the temperature difference from 32 degrees to 212 degrees Fahrenheit will be 180 degrees. And that will be 5,400 BTUs in total. The last step is figuring out how much heat is required to change it from water at 212 degrees Fahrenheit to steam at 212 degrees Fahrenheit. And in order to do that, we're going to use the latent heat of evaporation, which is 970 BTUs per pound. We have 30 pounds, so we're going to multiply 30 times 970, which is 29,100 BTUs. So we have to go through a number of steps to figure out the heat quantity at each of those steps. Now, to find the total heat required, we're just going to add up these 4 amounts. And when we take the sum of those 4 amounts, we will get a total of 39,000 BTUs to take 30 pounds of ice at 20 degrees Fahrenheit to steam at 212 degrees Fahrenheit. Let's now look at some questions where we might need to calculate the temperature difference or a temperature. In our next example, we know that 3,000 BTUs of heat are removed from 50 pounds of water at 150 degrees Fahrenheit. The question says, what is the new temperature of the water? So in this case, we know H, which is 3,000. We know the weight is 50. It's water, we know the specific heat is 1. What we don't know is temperature difference. I'm just going to multiply 50 times 1, which is just 50. And we're solving for delta T. So it's like an X, and if you prefer to use an X, that's fine. It's being multiplied to 50, so in order to isolate, we're going to divide by 50. Whatever you do to one side of an equation, you must do the same thing to the other side. So by dividing the right side by 50, it will cancel, and I've isolated delta T. And then on the left side, 3,000 divided by 50 is 60. Now that's not the temperature, that's the temperature difference. We want to know the new temperature of the water, so we know that it's going to decrease by 60 degrees. So the new temperature will be equal to 150 degrees Fahrenheit minus 60 degrees Fahrenheit, which is 90 degrees Fahrenheit. Now let's look at an example where we're finding the final temperature, but the substance is changing form. Our next question has 18,000 BTUs of heat being removed from 60 pounds of water, which is at a temperature of 150 degrees Fahrenheit. We want to know what form and temperature will this water have. So if we were to set it up the way we did in the previous example, 18,000 is the heat, weight is 60, specific heat of water is 1, and what we don't know is the change in temperature. If we divide both sides by 60 to isolate delta T, we're going to get 300. If we were to take 300 away from 150 degrees Fahrenheit, we're getting into the negative temperatures, which obviously means it's ice, but we can't forget that it goes through a change of state. So this method is not going to work when we have a change of state. We need to do this in steps. So what we're going to do is find out how much heat is required to change this water from 150 degrees Fahrenheit to 32 degrees Fahrenheit, and that will be the weight times the specific heat of water times the temperature difference from 150 degrees to 32 degrees is 118, which is 7,080 BTUs. Now we're going to find out how many BTUs must be removed to change it from water at 32 degrees to ice at 32 degrees. And in order to find that, we're going to use our latent heat of fusion and multiply by the weight of 60 pounds. So 60 times 144, which is equal to 8,640 BTUs. And now we're going to add those two amounts up. So the total heat that must be removed to change this amount of water to ice at 32 degrees is 15,720. We're continuing to remove more BTUs than that, so let's find out how many more BTUs need to be removed to then figure out how cold that ice is going to be. When I subtract 15,720 from 18,000, I get 2,280. So that's how many BTUs are yet to be removed from the ice. So let's figure out what the temperature of the ice will then be once those are removed. We're going to use this formula. The heat is 2,280 BTUs. The weight is 60 pounds. The specific heat of ice is 0.5. And we're going to find change in temperature. Let's simplify first. 60 times 0.5 is 30. And in order to isolate change in temperature, I'm going to divide by 30. What I do to one side of the equation, I have to do to the other side. 30 will cancel, and I will get change in temperature equal to 76 degrees Fahrenheit. So that's how much the temperature of the ice will decrease from 32 degrees Fahrenheit. So now, last step, let's find the temperature of our ice. It's going to be 32 degrees Fahrenheit minus 76 degrees Fahrenheit, which will be negative 44 degrees Fahrenheit. So the answer to our question, it will be ice at minus 44 degrees Fahrenheit. Let's look at one more example. This time it's going to be two quantities of water that are mixed together, and we're going to find out the final temperature of that mixture. In our last question, we have 25 pounds of water at 120 degrees Fahrenheit mixed with 40 pounds of water at 50 degrees Fahrenheit. What is the final temperature of the mixture? What will happen is these two amounts of water will mix, and the cooler water will warm up to a certain temperature. The warmer water will cool down to that same temperature. And the equation that we're going to use to find this is the heat gained by the colder substance will be equivalent to the heat lost by the warmer substance. The problem with this question is we don't know the temperature difference for each of those heats. They're going to be different, so we can't let temperature difference be our variable. Instead, we're going to let X be our final temperature. And we're going to have to write our temperature difference in terms of X. So first of all, let's look at the heat gained by the colder substance. We have 40 pounds times the specific heat of water is 1 times the temperature difference to go from 50 degrees Fahrenheit to X degrees Fahrenheit. Always write it as the higher temperature minus the lower temperature, so it will be X minus 50. That's going to be the temperature difference for that cooler water. Then the heat lost by the warmer water will be 25 pounds times the specific heat of 1. And then the way that we're going to express the temperature difference of the warmer water, it's going from 120 degrees Fahrenheit down to X. So we write that as 120 minus X. So the order is very important. This involves a little bit of algebra to solve. I'll go through the steps and hopefully you'll be able to follow. I'm just going to write this as 40 times X minus 50 equals 25 times 120 minus X. In order to solve for X, I need to eliminate these brackets. So I am going to distribute the 40 to each of these terms. So I'm going to get 40 times X, which is 40X, minus 40 times 50, which is 2,000. I'm going to do the same thing on the other side. I'm going to multiply 25 to each term in those brackets. So I'm going to get 3,000 when I multiply 25 times 120, minus 25 times X is 25X. I've got X's on this side of the equation and X's on this side of the equation. I'm going to move all the X's to one side and my numbers to the other side. In order to move this 25X, I need to add 25X to this side and it will be equal to 0 and it will be gone. And I then need to add 25X to this side. In order to move this 2,000, it's being subtracted, so I do the opposite. I add 2,000 to this side, and it will equal 0. And I have to add 2,000 to this side, so I'll have 3,000 plus 2,000. Now I can combine 40X plus 25X will be 65X. 3,000 plus 2,000 is 5,000. And now to solve for X, I'm going to divide both sides by 65. And my answer will be 76.9 degrees Fahrenheit. That will be the final temperature of that mixture.